Good morning, everyone. Welcome to the next Blue Waters webinar. My name is Maxim Belkin, and it is my pleasure to welcome you to the webinar titled Hyperglyphs, Exploring the Limits of Glyph Structure. Today's webinar will be presented by Jeff Sale, who is currently a learning design technologist at the San Diego Supercomputing Center. Without further ado, I'll turn it over to Jeff.
Thanks very much, Max. I really appreciate the opportunity to show the group joining me the work that I've been working on for the last several years. So briefly, here's what we have planned. This is a 2-hour session, and I have a reputation for trying to pack too much in, and yet there's still quite a bit of material that I'm leaving out. So hopefully there's considerable interest that I'll generate from this presentation, and you can communicate with me after this webinar for more information and maybe some insight into some of the other work that I've been doing. So we're going to go through a brief background of what led up to this presentation. It's based primarily on the concept of glyphs, so I'll go through a brief history of glyphs, and then I'll just give you a rough idea of where I've been for the past few years working on three-dimensional glyph design. I will be using a tool that's an open source tool, but my focus will be more on the concepts than the actual application. I think you'll be impressed by the application. It has some strengths. It has some weaknesses, but overall, it's a pretty powerful little 3D visualization tool. We'll talk about basic glyph structure, the kinds of features that one might look for in a hyperglyph type of structure. And then I'm going to go through a series of demonstrations of using a hyperglyph concept to visualize a variety of different data sets. And if Murphy is alive, fingers crossed Murphy isn't alive and well, and this will go smoothly. But considering I'm going to be trying to do some real live demonstrations, you just never know what's going to happen. So let's carry on. And I want to emphasize that you should feel free to post questions to the chat anytime throughout the presentations, but I'm hoping to be able to leave a little time at the end for question and answer. Okay, so a little bit about me. I was born in Canada, but I've lived in the US for most of my life. And given the current political climate, I'm actually trying to naturalize. And I'm hoping that I'll be done with that process sometime later this month. Very excited about that. My background is in applied physics, and I also did some graduate work in neurophysiology, and I'll talk a little bit more about that. But recently, I got a master's in learning design and technology, which is formerly education technology, because that's really where my passion is, in education and trying to nurture future cyber geeks to do the same kinds of things that we love. Of course, I'm highly motivated by my family. That's my wife and daughter. Trip to Hawaii. A little bit about one of my favorite things is backpacking. A couple of years ago, we did the John Muir Trail. And I always feel like a bad day fishing is still better than a good day working. Even when it's raining out there, it's pretty spectacular. I also do art. These are just a few examples of some of the art that I've done. In general, the San Diego Supercomputer Center has a lot of closet artists. It's interesting, when they come out of the woodwork, we have an annual art exhibit, and a lot of the cyber geeks really show off their artistic side. But I did a couple of works that are sort of relevant to this. The image on the left is a mural that I did of Michelangelo's David, and it led to a friendship with a gentleman by the name of Dave Warner, who's really the visionary behind this whole presentation that I'm giving. The mural on the right is something I did with a fraternity brother, Steve Overland, who went on to design the Cray T3D and the T3E supercomputers. When I was at University of Minnesota, he was a fraternity brother. So it's interesting how supercomputer geeks can also have a little bit of artist in them. My full-time job at the Supercomputer Center is focused on education, outreach, and training. I help develop tutorials for our users, as well as I support our K-12 outreach programs, teacher tech and student tech. and I work on supporting and maintaining our online web presence with a variety of different courseware applications. My love, though, is creating interactive models and simulations for learning, taking a complex concept in science and turning it into some kind of interactive tool that will help science and math students understand better. And my visualization work is mostly work that I do on the side, and I'll get more into that. But I have a strong background in virtual reality and applying virtual reality technologies in medicine and the clinic. Many years ago, we were working on applying the virtual reality data glove from VPL Research. Many of you out there might know the name Jaron Lanier. We were working with Jaron to try to get this glove to work on patients, such as Parkinson's patients, to really do quantitative assessment of Parkinson's tremor. Up until then, and this was about 25 years ago, up until that point, physicians really used a 1 to 10 scale and had to rely on their memory and recall to really gauge a patient's progression or digression. And putting the glove on patients allowed us to, I guess, validate or not necessarily virtual reality technology's role in the clinic. The glove really wasn't designed for that level of detail, but we've pushed the technology and have helped advance quantitative assessment in medicine. At the same time, I was doing a lot of visualization work with data collected from patients, EEG and ECG, physiological data. And I mention that because this talk really stems from a lot of the visualization work we did earlier. So I want to call out Dave Warner, who's a close friend and colleague, as really the visionary behind a lot of the work that we did. These are a couple of scribbly diagrams that came out of Dave's brain, and he had a vision of trying to map some of this stuff into an actual virtual reality. My background and strength was visualization, but we felt that visualization was in some ways overwhelmingly dominant in scientific research. And the entire human body has ways of interpreting and processing information. So we sort of felt like we were being photic chauvinists by focusing so much on the visual system. So we got into other types of technologies for different types of sensory systems, auditory and haptic, those kinds of things. But I want to mention that Mark Pesce, who was the developer of the virtual reality markup language, VRML, was inspired by the concept of perceptual cybernetics, and it led to a lot of the pioneering work that he had done in VRML. So the work that I'm going to show you today goes back many years, a couple of decades, and has its roots in some of the earlier virtual reality work that we had been doing. At Loma Linda University School of Medicine is where really all of this started. We established a lab we called the Neurology Research Lab, and the team we referred to as the NERT team as opposed to INERT. And this is just the usual suspects who are involved in that effort. So I just want to make sure they all get a little bit of credit for some of the work that I'm going to be showing you. We also pioneered different ways of applying medical education technology to the School of Medicine's curriculum. And 25 years ago, 3D models of the brain were wholly new, and a lot of our physicians were thinking that this was just a flash in the pan. But things have changed, and now 3D anatomy has really become a pretty standard fare in medical education. Our work in virtual reality in the clinic got a lot of attention. We were covered by a lot of news stations. And if you go to YouTube, I'm not going to take the time to play a YouTube video for you. Playback in WebEx isn't that great. But if you do a Google search in YouTube on Dave Warner and virtual reality, you'll see some pretty inspiring videos of some of the work we were doing with quadriplegics who are paralyzed from the neck down, putting electrodes on their face to allow them to control a computer with their face muscles, allowing cancer patients who are in the intensive care ward to be able to experience virtual worlds. And we got so much attention that James Clark, some of you may or may not recognize the name James Clark. He was the visionary behind Netscape, went on to become a multi-billionaire. But at the time, we were doing a lot of our VR stuff. He was running Silicon Graphics and reached out to us and actually visited our lab to talk about adapting the tools that were in the visualization tool that we worked with, AVS, to an SGI platform. And that led to a sort of a clinical emphasis of one of their visualization tools they called the Data Explorer. But in the interest of extending beyond visualization and moving more towards a term we call perceptualization, we developed a variety of different technologies, sort of you know, shooting from the hip. This in the lower left-hand corner is a remote control car with a camera and a microphone attached to it, and we gave it to a kid who was a quadriplegic, paralyzed from the neck down, so he could control it and navigate through his house and through his neighborhood and get to experience the world in a little bit more convenient way. And one of the surprising outcomes of this also was that his siblings, his brothers and sisters, could grab the car and take it around and give their brother a tour. And in the lower right is a demonstration. That's Dave sitting next to a chair with a bunch of pins sticking out of them, and he's controlling those pins with his forearm muscles. So this is one way you can sort of give yourself a back rub yourself. Okay, and then Dave went on to Syracuse University to do a NASON fellowship and developed a number of technologies that tried to integrate sensors and other types of data into a whole system that we called Neat Tools. And Neat Tools was used in a variety of different applications to allow quantitative assessment and environmental control in the same ways that I've already talked about. Okay, and then Dave went on to Afghanistan, and this is sort of what led to the tool that I'm going to demonstrate. He was working and bridging the gap between civilian and military responses to natural disasters and also to the war that was going on in Afghanistan. And he recognized the serious lack of command and control systems that provided insights into situational awareness. And so a lot of this led to his vision of the tools that we're going to demonstrate. So these are some sort of concept pieces of how he would envision a command and control display to be used to represent information of large, complex events distributed globally. And ultimately, this has led to a spin-off startup company called Glyphs. Glyphs has taken the open source tool that I'm going to demonstrate and adapted it into a two-dimensional graphical user interface and tried to map it onto specific needs of the community in Washington, D.C., government agencies, the Department of Defense, and those kinds of things. So we're very excited that the tool has actually led to some very successful spin-offs. Okay, so since this presentation is about glyphs, I thought I would briefly go through a history of glyph design. Obviously, tens of thousands of years ago, petroglyphs were where it all began, hieroglyphs, and then Mayan symbols, Enochian symbols, and then even to modern day gaming types of symbology, and of course our favorite emojis. All of these sort of fall within the category of glyphs because they contain information, they conform to a convention that people need to learn to understand and interpret. And I included these as well just to sort of stimulate some thought. Nature in many ways can emulate math. The images on the left are three different modes of information. On the far left are sacred geometries, in the middle are astronomical images, and on the right are biological cell-like structures. And then on the far right are other types of biological organisms. But if you do a search for what is a glyph, Wikipedia basically defines it in the context of typography. There is absolutely no reference to glyphs as they're used in visualization. So I was kind of surprised to see that. Also, Google turns up a definition as being a hieroglyphic character or a symbol, a pictograph, or an ornamental carved groove or channel as on a Greek frieze. So still no reference to the term used in visualization, But I thought the graph at the bottom was interesting too, the use of the term glyph over time. There are a couple of peaks in the early and mid 1900s, and then it sort of tapered off. And glyphs, given that they carry information, could be compared to terms such as grapheme and morpheme. I would say it's not necessarily related to something like a phoneme, which is really a sound that carries information, but why not? At some point, we might be able to integrate those kinds of things within auditory oralization of data. Just one real simple example of a classic glyph. Many of you may already be familiar with the wind glyph, and that's not the little puffy puff of smoke there. Wind glyphs have been around for many decades. They're basically defined with a direction and a magnitude, but the magnitude of the wind is identified by little tiny tick marks that extend off the tail of the glyph. WonderMap actually uses that kind of structure in their weather map, but I can't say that their wind glyph structure really shows much consistency and alignment compared to the lower left-hand corner, which is more of what you might expect with a wind visualization. I also want to acknowledge previous work that has inspired this work. A lot of work has gone into using various glyph designs to enhance visualization. This article in particular is a very comprehensive article that deals with foundations and guidelines and techniques. And so in the upper right-hand corner, there's some good examples of the different types of qualities, visual qualities that can be used to differentiate one object from another. The article also includes a nice list of channels, what they refer to as channels for variation of glyph structure. All of these are in the context of visual modifications to a glyph. And then they get into ways in which a visualization may be more or less one feature or another, such as whether a channel's capacity can be greater or less, an object's searchability, visual order of structures and those kinds of things. In the lower left-hand corner is an example of the principle of small multiples. And in the lower right-hand corner is a good example of a two-dimensional glyph that shows variation in structure of a particular mechanism. I also want to talk briefly about the idea of the principle of small multiples. This was first described, as far as I'm aware, by Edward Tufte, a visualization pioneer who you probably are aware of. The idea is our brain can process small changes in a pattern over a large area. So sometimes it's best to let the brain do what it does best and just present the information and leave it available for interpretation. So that's maybe a good example of what I'll be demonstrating in just a few moments with the visualization tool that I'm working with. Some of you may be familiar with Chernoff faces. This is another sort of concept similar to the principle of small multiples. The idea is that humans can recognize features of a face and emotions and those kinds of things with very subtle detail. So Chernoff faces have been used to visualize variations in different types of data as well, with greater or lesser success. But I thought it was a real interesting attempt at sort of veering beyond traditional glyph types of structures. Now, I had used the principle of small multiples many years ago in doing visualization of topographic brain maps. The tradition was that a neuroscientist or a neurologist would look at a small sequence of two-dimensional brain maps and try to piece together the structure, the dynamics that are going on in the brain as a result. But it's difficult with a certain high number of small multiples to really put an image together. So I had the idea of piecing those 2D topographic brain maps together into sort of a stack or a loaf of bread and use the idea of isosurfaces, or the feature of isosurfaces in many visualization tools, including AVS, to visualize volumes of electrophysiological data. Now, I talk about that because a lot of what I'm going to show you deals with data that's visualized in both space and time. And this is a classic visualization done 2 centuries ago that shows the progression of military campaigns, one by Hannibal, another one by Napoleon. And it's also a multivariate type of display. It not only shows time, but it shows change in space. So the concept of space-time cubes has now become a fairly standard approach. In fact, it's an official option in ArcGIS to visualize spatiotemporal data. There's a number of good resources. I reference one down in the lower left that provides a really nice comprehensive summary of space-time cubes and spatiotemporal types of visualizations. The one that we're looking at on the left is of athletes and their movement over time on a basketball court. Okay, so the tool that I'm going to show you has actually gotten some good attention. Robert Steele, highest ranking civilian of the CIA, when we showed it to him, it blew his mind, honestly. The tool certainly gets reactions. The idea of hyperglyphs in the context of what I'm going to show you, usually people are not neutral. They either love it or maybe not so much. And the idea of visualizing both the forest and the trees, I think, has emerged from some of the work that I've been doing. In visualizations, frequently, if you have a massive amount of data, you'll only be visualizing one point at a time, and then hundreds of thousands of those points. But the points are basically just dumb points. Well, a hyperglyph turns those points into semi-intelligent structures of embedded information. So in a sense, the hyperglyph is a forest itself, and you'll get a better idea what I mean by that in just a few moments. So these were some first attempts at creating glyph structures to represent different things like the nutritional content of McDonald's distributed throughout San Diego County, or the tourist types of data along tourist locations along the coast. So the tool that I'm going to be demonstrating is affectionately referred to as ANTS because of the first work that we had done in visualizing Scopus citation search results of ant research and sociobiology. Shane Saxon gets credit for being the lead developer. I'll show you links to the tool itself, but once again, I want to emphasize that I'll be talking more about concepts than the actual tool. It's been described as toroids on steroids, or spreadsheets meets cyberspace. Features that are really important that characterize a hyperglyph include interactivity, multimodal information such as color and shape and size, multidimensional, parent-child relationships down many levels. The hyperglyph should have a dynamic capability, and it should be capable of supporting embedded information. So here's some useful links. Hopefully we'll be making the PowerPoint presentation available for you to download. I'm not really sure how best to accomplish that, but I can certainly make that happen offline. There's links to archives of photo galleries of examples of some of the work that we've been doing, some YouTube visualization, YouTube videos, tutorials, and those kinds of things. And it might be useful at least to bring your attention to a couple of applications that appear to attempt to address the same kinds of visualization needs. One is GioTime, and the other one is Datascape. Both of these sort of work within a space-time visualization paradigm, provide a high degree of interactivity. They both come with a 2D graphical user interface, whereas the tool that I'm going to show you does not in the traditional sense. Okay, and I also want to make the case for toroids. This tool uses toroids as sort of one of the default geometries. And this is a great visualization of the use of circles in 2 dimensions, instead of using solid circles, which would obscure data points that overlap, they use just circular outlines. And then they also use transparency to really bring out highlighted features of things of interest that they want to bring the viewer's attention to. And the same kind of principle applies to some of the work that I'm going to show you as well. The toroid can be computationally intensive, so I try to avoid using it if I'm working with hundreds of thousands of geometries in a space. But it can also be useful in showing connectivity between different subgeometries. Okay, so how we're doing on time? We're about a half an hour into it. Okay, so I'm going to go through a brief demonstration of the basic ideas behind the tool, and then show you some examples of visualizations that I have done. The very first visualization that we attempted about 4 years ago was of Scopus search results, about 17,000 search results on ant behavior, sociobiology, and self-organized criticality. And the Defense Technology Information Center's database, which is a sort of a self-contained citation database hosted by the Department of Defense that has defense-specific types of citations in it. And my approach to this database is a little different than the one from the Scopus search results. Let's back up and look at this very briefly. The tree, so to speak, in the lower left-hand corner is a very simple glyph structure of sort of a squashed sphere with a squashed toroid extending off of it. The yellow toroid, the size of the toroid represents the number of citations of that particular article, how many times it's been cited by other articles. So let's go ahead and bring this one up. I'll go ahead and launch the tool. And I don't necessarily mean for this to be something you should be trying to do at the same time. The tool is developed primarily for the Windows platform. There are versions for Mac and Linux, but they have not been kept up as current as the Windows version. But actually, I realize I'm getting ahead of myself here. I haven't really demonstrated the tool. So let me back out and start over. Oh, here I go again. Let me try this again. Okay, so you should be seeing a blank space with a grid. Blue lines making up the grid. We go full screen. And then I'm going to hit the N key to create a new object. Now my frame rate is about 30 or 40 frames per second, but I realize through WebEx and YouTube, the frame rate will be potentially quite a bit slower. So I'll try not to navigate too quickly. In the upper left-hand corner is a series of menu options and feedback as to the XYZ coordinates or the scale or rotation values of the particular geometry. I can grab this geometry and move it around. I can right-click and raise it up and lower it. I can change its color. And you'll notice the toroid sitting near the top of it is a child object. So when I move the pin object, the toroid goes with it. But I can also grab that toroid and move it. Right now I'm moving it in the X direction. Now you might think that's vertical and Z direction, but right now this child object, this toroid, is moving within the parent object's topology. So one of the interesting things about this tool is each geometry can have its own type of spatial topology, the way its children are distributed around it. So if I hit the J key, with the parent child selected, it will cycle through a series of, I believe, 12 different types of topologies. This one is called the rod topology, which is sort of like a shish kebab way of distributing child objects. This one is called the point topology. And then a Cartesian coordinate grid topology, where the child geometries sort of move around in the same way the parent geometry moves. A topo called Z-cube. I'm going to cycle through here fairly fast. A couple more. This topology is called a sphere topology, which is very much like the Google Earth KML type of format, in which latitude, longitude, and altitude are default values. So when I grab this child object and move it around, it moves through a positive 180 degree values to a negative 180 degree values for the x direction or longitude. Latitude, it moves through 0 to 90. And then elevation. We can actually raise it up and lower it based on altitude values. So this kind of topology is very useful when you are visualizing geospatial data around a particular planet or type of structure. And then there's a toroid topology, in which the geometries sort of work their way around the outside surface of the parent object. A cylinder topology. Oops, I changed the child object. Cylinder topology, and then back to the pin topology. So the child objects topologies can be changed just like the parent object. I can cycle through the child object as well. And that child object, let's go back to making it a toroid. That child object can have children added to it as well. So if I hit the N key multiple times, I'm adding children to that child. I can select one of those children at the N key to that child. We can continue down about 30 levels of parent relationships. When it comes to actual data visualization, I don't need to go much deeper than 5 or 6 levels. Even that, the complexification can get a little overwhelming. But this kind of capability is now I have several objects in space. I can hit the tilde key to select all of them. And if I click and drag the parent object, as I drag it in the X and Y direction, the children will also move in the X and Y direction. Oh, I see. I got a chat saying you're losing my signal. Is that the audio that you're losing? Okay, now it's better. Great. So with multiple objects selected, depending on what I am doing to manipulate them, all objects will be manipulated simultaneously. If I want to scale them larger or smaller, I can choose the size object in the panel on the left, click and drag. Oops, it shifted to topo. Didn't mean to do that. And then I can click and drag and scale these objects. Let's go back to the torus topo again. There we go. So if I click and drag, then all of the geometries will get larger or smaller. Likewise, I can cycle colors for all of them. I can deselect some sub-objects by right-clicking them so that they aren't affected. So when I cycle colors, they don't get modified. Okay, I'm going to go ahead and delete this object and actually load a file that contains sort of a display of all the different topologies simultaneously so you can see how this works. So here I have in the lower right the cube topology, then the sphere topology, the toroid topology, cylinder, pin, rod, point, and grid, and then the Z topologies, which center the child objects in the middle of the parent. But you'll notice each one has a child object that's colored white. What I want to do is actually select all of those child objects, and I can do that by hitting the return key and typing. You'll see in the lower left-hand corner, actually you may not be able to see that. I should move this up a bit. Okay, that should be better. So I can select a particular branch level, and all geometries on that branch level will be selected. Now, if I want to move them, I can grab one and move them, and all of them move. So right now, I'm moving them in X and Y directions, and depending on the topology of the parent object, the children will be moving in a way constrained by the topology of their parent. Generally, this is kind of hard to wrap your head around what's really going on. It really starts to sink in when you see how data can be visualized with these tools and how they can actually be visualized dynamically and interactively. Okay. So there's a real simple example. I'm not sure what else I really need to cover. Oh yes, I didn't really talk about all the different geometries that exist. So let me just cycle through. There's a series of 19 geometries. Right now we're on the octahedra. If I hit the O key, it'll cycle through wireframe and then solid geometries of a set of 10 geometries. So this is a tetrahedra, dodecahedra, the pin geometry. Oops, I'm zoomed in too close. Cylinder, cube, sphere, cone, toroid, and that actually I think is the dodecahedra. And then back to the octahedron. Okay, so there's a number of different geometries. Now the tool also does support importing 3D models. I don't really have demonstrations of doing that, but I can demonstrate how it's done very simply. I do have a number of different demonstrations. I hadn't planned on showing any of them because this presentation is really about hyperglyph structure. Okay, so let me close this one out. Now I'm going to bring up the Scopus search results visualization of ant research and sociobiology. And we'll just do a little bit of exploring here. Okay, so what we're looking at is spatiotemporal data. You can see the map. Oh, I'm sorry, you can't. Let me escape out here and go full screen. Okay, there we go. Now we have a map. Each one of these geometries, if we zoom in here, is a flattened sphere, and it represents a particular article in the search results. If I hit the I key, I can actually see the journal that article was published in, Physical Review Letters. Shows the author's names, the year, and the title. This one, oh, I went too far there. Tracer dispersion in a self-organized critical system. Okay, so these were geocoded based on the institution that the primary author was located at. So there's a big tower of geometries right here, if we zoom in on it, that is at latitude and longitude 0, 0, because my geocoding didn't have sufficient information to give those an accurate latitude and longitude. Many of you who have tried to geocode data based on kind of questionable address information are very familiar with this tower of geometries in a space-time visualization over latitude, longitude 0, 0. But I thought I'd leave it in there. It's useful information, even though it isn't geolocated. So let's take a look at the view from the side. From bottom to top is time. Each one of these articles had a particular year of publication. So I visualized them based on that. And if we look in the lower left here, this geometry is really the most prominent one of the entire visualization. And it turns out actually that this represents an article that is very close to my heart and work that I had done, and some of you may actually even be familiar with it. It was sort of the foundational article on self-organized criticality by Purbach, Tang, and Wiesenfeld. And it really sort of started things off. So you can see it's relatively low in the visualization. It came early on, although there are a few other geometries. One thing I'm going to do is maybe try something just for fun. There's a select region option in this tool, and if I select everything down in the lower area and hit the I key, I can visualize key bits of information from these articles. We can get a sense of the journals that we're primarily publishing prior to the self-organized criticality article. Okay, let's turn those off again. Now, each one of these geometries actually has a child geometry connected with it. If I arrow through the parent-child hierarchy and hit the H key, I can expose that child object. Now, these parent geometries are already scaled to the size corresponding to the number of citations of the article. But I added, as extra emphasis, this sort of child object to give the overall visualization a little bit more oomph, so to speak. So I'm going to hide that, and I'm going to select all of those branch level geometries. Actually, okay, there we go. And then I'm going to unhide them all. Now, if we zoom back, we get a sense of change over time. I grab a good geometry here to view from. Okay, the primary article that sort of set off a lot of activity and research over the course of time vertically. Actually, let me zoom in here a little bit closer. There seems to be a peak of activity right around, let's say, the year where this article, 1996. And then as we go up higher to more recent activity, there have been a lot of publications, but not a lot of citations. So keep in mind the yellow squashed toroid represents the number of citations. So it seemed to have a peak here. So this is sort of what I mean by visualizing the forest and the trees. We can zoom in and get more detailed information from individual geometries, and this is a fairly simple glyph design. But we can also zoom out and see how information changes over time. So this is the kind of vision we have for maybe doing explorations of citation databases in the future. Okay, but we don't really have any way of characterizing the content of these articles in terms of topics. And that's what I'd like to show you next. There's been some work in the last several years of topic space research, what with social networking data becoming more available. So I'm going to show you a real simple example. Well, maybe not so simple. And actually, let's go back to the PowerPoint and take a look at this glyph structure first. Okay, so in the upper left-hand corner is a parent geometry, which is a wireframe sphere, then a child geometry, toroid, The toroid really serves the purpose of connecting its children together, because when you visualize all of these geometries in a single space, it helps to have that sort of connectivity, this visual connectivity. And then there's 7 third-level child objects that represent the degree to which that particular abstract of the article falls within one of the topic categories, such as physics, chemistry, biology, geography, engineering, military, and social. The way I did this was I went to a Wikipedia page on physics and did a word count of all of the words on the physics article in Wikipedia, and then I sorted that word count by frequency and extracted the top 100. I eliminated stop words like the and then I used that sort of as a word vector that I correlated with the abstracts of these particular articles in the DTIC database. And then the frequency of occurrence of words within that particular abstract corresponding to that particular topic are scaled. They're scaled to correspond to the frequency of occurrence. So let's take a look at the search results. Searching the database for the term cyber. Okay, so this is a very similar visualization to what we were just looking at. These are global visualizations. The geocoding is based on the address of the institution of the author. Vertical is time. And actually, I think I clicked, yeah, I want to select the very first article. Oh yeah, you're not seeing it. How'd that happen? Thank you. Okay, there we go. Sorry about that. Okay, the very first occurrence of the term cyber in the DTIC database occurred back in 1950, titled Correlation Functions in Communication Applications. This one seemed to have correspondence with all of the different topics, with no real dominant topic. You might say physics, which is red, and biology, which is blue, I believe. But if we want to learn more about that, this particular visualization tool has a really nice feature. If I hit the U key, and we'll see if Murphy is alive and well. Yeah. Each visualization has the capability of calling a web URL. In this case, I'm calling a PHP script that takes an ID associated with that particular geometry and uses it to search the database for that particular article. So here I've got the article listing the title, the authors. If I do a search on the term cyber, we can see that it occurs in the keywords and in the abstract. So this is a really great way of drilling down and learning more about individual citations, because there's only so much information you might be able to pack into the embedded information associated with that glyph. But one of the other really interesting things about this particular visualization, and maybe you can notice it, there's a couple of things going on here. Most of the articles are, of course, are affiliated with the United States. You can see vertically we're aligned with mostly East Coast and West Coast, a little bit going on in the Midwest. Some publications in Europe. But there's a gap. You'll see that gap right there. I'm not sure I can explain why there is a gap. And that gap occurred back in, well, let's zoom in here, roughly, let me select the parent object. That gap is around 1993. And then what you'll notice, after 1993, vertically up to about the year, I think this database goes up to about 2010, is the very, very dominant yellow color, which corresponds to military. So at some point in 1993, the concept of cyber, probably affiliated with cyber terrorism, really started to dominate the citations in this particular database. So that was a really interesting surprise. This is the kind of thing that we hope this kind of visualization approach can provide. Of course, maybe 7 child objects is too many. There's a lot of information here. Some of the feedback that I've gotten from people that I've demonstrated this to, they feel like there's just too much information. So that's a judgment call. Glyph design is sort of an open field right now, and we're exploring the limits of it. Okay, so when I've been showing this tool to some folks, I jumped too quickly to complex data sets, like the ones I just showed you. And I wasn't necessarily well equipped with a story to tell. But I teach part-time at a community college. I teach web programming, and we use Moodle. Some of you may be familiar with Moodle. It's a learning management system that's become very popular. It's an open source learning management system. And we host our own Moodle site, my wife and I. We sort of tag team teaching courses at a local community college. And that's a database that's really familiar to me. So I thought I'd like to see what an entire course's worth of student activity might look like in this tool. And I was not only interested in my students' performance, but I was interested in actually being able to drill down to the individual activities that they were performing throughout the semester. Okay, so this class was taught, make sure you're seeing what I'm seeing. This class was taught back in spring of 2012. Let's load the data. Now in this space, this is not geocoded information by any means. It's an entirely different data set. You'll see some labeling on the grid. Hopefully Murphy's going to cooperate here. I'm not getting any response. Performance is going very slowly. Not sure what's going on here. There we go. Okay, now it's speeding up here. And I need to go full screen again. Okay, so what we're seeing here, if we look at it from this direction, it looks sort of like a giant slalom course. You'll see sort of a stair-stepping feature. The vertical direction represents actual time, so that's similar in a sense to the previous visualizations. The axis from left to right corresponds to individual student IDs or Moodle user IDs. And if I zoom back here a little bit, my frame rate is pretty slow, but yours may be even slower. Moodle user ID. So as users were added to the Moodle database, they get a particular ID. You'll see they're not evenly spaced. Most of the users are grouped around a small subset of user IDs, but that's just happenstance. Doesn't really impact anything. It's just an easy value to use to graph this data. And so an individual student corresponds to sort of a vertical distribution that goes off into the distance and vertically. So for example, I've selected a student right now represented by yellow, right in the midst of a number of blue students. The color corresponds to the actual final grade that the student received in the class. I do have a legend here, cumulative points. I'm using a rainbow gradient. Purple and blue are failing. Cyan is maybe slightly above D. Greenish and yellowish are C's and B's, and orange and red are A's. So we have mostly, I would say, A and B students. Interestingly, there's a little grouping of C and D students, these blue geometries, sort of grouped together. No good explanation for that. They were all added to the Moodle database at the same time, and they had roughly similar performance, but you'll see some A students intermingled in there. Now, because this was a hybrid course, some of the students met face-to-face and some of the students were entirely online. And the reason we're seeing this stair-stepping, and I'm going to look at it from the side here, is because since time is vertical, this means that a lot of events, like in this area right around here, occurred in roughly the same time. These are all students whose activity occurred in class, face-to-face, all at the same time. They were given assignments at the same time. They were encouraged to interact on the discussion forums at the same time. So that's why they all sort of form this layer. And that is the primary cause of this sort of slalom, stair-stepped appearance. So this stair-stepping was sort of a surprise to me, and you don't see it in courses that are entirely online. I do teach some courses entirely online, and their curves are pretty much a gradual slope. Another feature, another part of the story to tell, you may notice where my cursor is, if you can see that, there's a gap here, vertically. A lot of time went by with no activity. Given that this was a spring semester, 3 guesses what that is. That's spring break. Most students were not doing anything. However, there is a student who actually got quite a bit of work done during that time. Now that student, actually in the cyan here, cyan suggests that they still didn't end up getting such a great grade, maybe a C, but they were clearly active during spring break. My guess, and actually it turns out this is a single mom who's working and she doesn't have a whole lot of time. So spring break was a real opportunity for her to get caught up. Now there's lots of other things I could say about the different types of structures in a global way about this data set, and that's the forest. But I'm really interested in what students did on an individual activity level. And so if I zoom back here for a moment, let's go back to the beginning. Okay, so these bottommost glyphs correspond to students in class on the very first day of class. And if I zoom in here really closely, you'll notice that there are child objects. Okay, so this, for starters, is a very simple glyph. I'm actually going to grab one and move it out of the way so we can look at it. So I'm just going to click this glyph and drag it to the right a little bit. I'm also going to hit the I key so we can see who this is. This is one of my students, Marticela Luz. This happened in January 31st, 2013. Actually, this was a 2013 course, not 2012. The course was 2012. And the activity that Marticela is performing is represented by this child glyph right here. So if I select that child glyph, we can see that she's viewing something. I do have a legend embedded in this world too, where we can get a quick idea what these activities were. So if we zoom up here just for a moment, we can see these event color coding. Viewing a forum post is dark gray. Printing a post is medium gray. Viewing forums in general is a pinkish color. Viewing a particular forum is bluish. Of particular relevance are when a student adds a post, or when they attempt a quiz, when they view a summary of a quiz. These are all activities in which they're engaged and they're doing something actively. And that's what I care about most as a teacher. So if we zoom in here and look at one of our A students, most of her activity is in viewing forum posts, but we can see some different colors here. And these represent doing the first quiz in the class. And what we assigned them was to actually do a survey. It wasn't really a quiz, but in Moodle, you use the quiz activity to perform surveys and those kinds of things. So we wanted to get to know what the students were all about, their existing experience. And then we actually did have them do another quiz. So a little later, same day, this learner actually submits an actual quiz. And then we can see even further to the left here Here's where they're actually doing things like adding a post to the discussion forum. Okay, so this gives me a great opportunity as a teacher to drill down and look more closely. Unfortunately, this database doesn't exist anymore. We've moved our Moodle site to a whole new hosting service. Otherwise, I'd be able to demonstrate the querying feature of being able to bring up more details of my users. So I can use this to actually go into my Moodle course and drill down into the actual course itself. Okay, I'm going to show you one other thing, and then I'm going to jump to I'm going to take a break. This being 2 hours, not a long break, but I wanted to show you maybe an artistic side of things just as part of the break. But one more thing I want to show you also related to Moodle databases is a visualization of an entire Moodle course site, not just a course, but this is a Moodle site that the Supercomputer Center hosted for many years. I think it was from about 2006 to 2012, where we made it available for teachers who did not have access to online learning management systems at the time. This was when learning management systems were not very common in high schools. Now they're pretty standard with tools like Canvas and Blackboard. Moodle's database provides a parameter called monthly averages for activity. And so that was a nice way of maybe not trying to visualize all student activity for all courses for all years, but maybe keep it a little bit simpler and just visualize monthly averages or monthly summaries. Okay, so I'm going to load the database. And this one might be a little bit difficult to view, and I'm going to try some tweaking to bring out the individual glyphs. And this is also going to be a bit of a challenge to describe. But first of all, I'm going to zoom in here. And yeah, performance seems to be slowing down a little bit when I load a database. I'm not sure why. Usually it's fairly responsive. Okay. Yeah, I'm being advised to turn off WebEx video. And I'm honestly not exactly sure how I should do that. So I'll wait and see if Max or Michael can give me some insight into doing that. Part of it also is that it's loading all the metadata that provides information, and it still hasn't actually loaded it all. But we're getting good performance now. Okay. So this is also a very simple glyph. There we go. Okay, so there's the metadata information. This glyph represents a particular summary of monthly activity. This happened back in 2006 in the month of August. It identifies the course ID as being the Teacher Tech Portal home, and there is my name. I was the first user. This is the first event of the entire server. That's why I'm in the extreme lower corner of this entire data set. I'm going to try to zoom out here and then pick another object, sort of orient the entire visualization. It's always a challenge navigating a 3D space. Some of you can relate. Okay, so I had actually downsampled. It's difficult still to see what we're looking at, but in the lower left-hand corner, that's the beginning of time, so to speak. From left to right are the actual users that were given accounts, and there's thousands of users. And then I'm going to orient this to look at from the side. And here, from right to left, are individual courses. So some courses had more activity than others. Some courses were individual courses that were given to teachers during workshops. And I'm going to show you some of those structures in just a minute. Okay. Well, honestly, I don't think that is the problem in the first place, so I'm not going to fuss too much. I'm not seeing a video button under the video, but thanks for trying. I think the performance issue really is not necessarily related to that. Okay, so let's zoom in to an actual course structure. Vertically is time, and because we see this row kind of distribution, we see these layers. Each one of those layers corresponds to a month. So this block of data here represents about 8 months, as you might expect, of a school year. The lowest layer, if we bring up a little label here, this was in 2007 and November. So their first month of activity occurred in November, and then December is above that, January is above that, February, March, April, May. And then the school year pretty much comes to an end. You'll also see, oh yeah, I didn't describe the individual glyph structure. So let me zoom into a glyph here. We downsample so I get slightly better performance. One of the nice features of this tool is the ability to downsample and reduce the number of objects so I get a little bit better performance. Okay, so this glyph represents an individual student colored based on the actual course. Because I'm limited in the number of colors and I have hundreds of courses, I have to reuse colors for different courses. But that's one of the prices to be paid for trying to render massive amounts of data at one time. And then the white child object, this is a child object. If I move the parent object, you can see the child object move with it. This represents the number of times the student performed a reading activity where they viewed a forum or they looked at a lesson or they viewed an assignment or something like that. And if I bring up the information, let me deselect here. This says that they committed 8 reads that month. I don't know if you can see that very well. And this label at the very end, it said reads :8. That means they had 8 reads during the month of December. Okay, so let's zoom back here. So this, as a teacher, gives me an idea of the level of activity of my students. I can also get a sense of what teachers are doing. There's also a feature that I like to call teacher towers. So let's see if I can select one of those back here. Yeah, okay. So in several locations in this database, you'll see these vertical structures. They're not blocks of large numbers of users over the course of several months. These are individual users who are active once a month for multiple years. And as you might suspect, these are teachers. So I call them teacher towers. Teachers typically will log in regularly, perform activities, design the course, update content, and there are several of them in this particular grouping. So I thought that was an interesting surprise when I visualized this database. I wasn't expecting to see that, and they really jump out at you. There's other structures that don't look like teacher towers and that don't look like actual full-blown courses. Let's see if I can grab one here. Yeah, this looks like it might work. When we see individual glyphs sort of arrayed one at a time in a direction, this may very well correspond to a workshop that we gave teachers. In this case, the teacher was the only person to log into that course, and they only logged into it for that one day during that 1 month. So if I select this particular glyph and highlight it, yeah, sure enough, the course ID is titled Moodle Series. That was a series of workshops that we gave back in 2008 to teachers to try to encourage them to use Moodle. And so those kinds of structures have their own unique kind of distribution. Teachers who emerged from those workshops very active and actually launched courses and used the tool regularly, you'll see a vertical tower sort of emerge from that initial workshop. Okay, so I'm going to stop here. Let's escape out. And now for something completely different. Let's go back to my PowerPoint. Whoops. Okay, I think, yeah, okay, so there's Teacher Tech, there's Moodle. When we come back from the break, I'm going to look at a couple of massive databases, one for you sports fans, the Layman Baseball Database. I'm going to show you how to visualize the entire database of batting statistics data from the beginning of Major League Baseball back in the 1800s. And then I'm going to show you the global actually, that's this slide, sorry about that. That has a fairly simple glyph that includes statistics such as home runs, RBIs, doubles and triples for the individual batters. Then I'm going to show you a visualization of the entire global terrorism database and show you maybe an example of a super complex glyph structure. But before we get into that, let me jump ahead here. Yeah, I'm actually getting kind of behind. I'm what you call a synesthete. I see letters and numbers in color, and I also see music. In a sense, I see music. When I hear a song, I get visual stimulation. Not sure why. Some of you out there might be familiar with synesthesia. It's not a syndrome or a pathology. It's just something that happens when one part of the brain is in very, very close proximity to another part of the brain, not typical for most people. Some of you may also be familiar with the Disney movie Fantasia, in which they actually did try to visualize classic works of music. And so that's what this is about. So I have a YouTube video that I'm going to encourage you to take a moment to watch just to get a sense of what this is about. Before we do that, I want to describe the glyph that underlies this. So let me bring that glyph up. There we are. Okay, so what I did, don't want to mess this up again. Let's make sure we're full screen. Okay, there we go. So I used MATLAB to process a particular song, one of my own favorite Tangerine Dream songs, and break up the frequency spectrum into individual frequency bands that correspond to sub-objects in this particular glyph. Now, this is a difficult glyph to fully understand, but each one of these spheres is a child object that corresponds to a frequency band, and I think I've broken the frequency bands up into about a couple of dozen frequencies from 20 hertz up to about 2000 hertz. So those of you who are familiar with frequency spectra and compressed spectral arrays, well, this is sort of my attempt at creating a sort of a musical, graphical play on music. Now, the video has actually synchronized the song to the graphics playback. And the playback uses a feature of this tool we call channels. So channels provides the ability to import data from a comma-separated values file that represents a stream of data. And in this case, it would be the stream of music data. And I realize now that I haven't really shown you what goes on behind the scenes with this file, or with this application, the ANTS application, and the simplicity of the data input files. So when we get back from break, I'm happy to go through that. In the meantime, just go ahead and browse to this web URL. There it is. There's a lot of things, like I said earlier on, that I won't be able to show you. And I've used this tool for pure art and math a number of different ways that I think you'll probably be impressed with. If I have a little time at the end, I can break those out. My goal here, though, is to focus on real data, real databases, and practical use of hyperglyph structures. So this next database that I'm going to show you is one of my personal favorites. It's a massive amount of data that I'm visualizing at one time, so frame rates really drop. But I'm going to try a couple of things to improve performance. Okay, but this is a database that's fully available. Anybody can go to Layman, I think it's layman.com or something like that, and download the database. So I've got it in MySQL. And when I create these visualizations, I use PHP. Strangely enough, it's not the greatest for performance, but I do a lot of my work through web-based forums to select different parameters. And let me make sure you're viewing what I'm viewing here. And once again, performance is probably going to be a little slow initially. Let me downsample here. Okay. There, yeah, performance is pretty good. So I'm going to navigate real quickly to more of a central location in this visualization. And then we'll upsample. Okay, so this is the forest. You'll see two blocks of a bunch of dots. On the left-hand side is the American League batting data, and on the right-hand side is the National League batting data. If I move a little bit to the right so you can see more of the National League. Now this is a few 100,000 geometries in the space at one time, so the fact that I'm even getting more than 1 frame per second is great. What I'm going to do, though, is cut the number of objects in half by selecting the entire National League. Actually, and I should show my geometry information. Is it not going to do that? Oh, yes. There we go. Okay. So I've selected an object. Happens to be Triz Speaker. For you baseball fans, you know who that is. The reason being I'll need an object that's relatively easy to reselect once I hide all of my other geometries. Okay, so I'm going to go up and choose Select Region. Oops. Once again, performance is pretty slow. Okay, so I'll click and drag and select all of these geometries. And then I'm going to hide them, and that'll speed up performance a little bit. And then I'm just going to focus on the American League. Oh dear. Oh, I just missed. That's what I get. Hold on here. When I select one object, I deselected all the other objects. Okay, so let me do this again. Okay. There we go. Okay, that was a little bit more difficult. Went better during practice. Okay, so now we're just looking at the American League, and let's zoom in on the individual, so to speak, trees of this database. These are individual glyphs that represent an individual batter's performance during a particular season. So right off the bat, I've singled out one player. Vertically is their career. The bottom geometries are the early parts of their career. The upper geometries are the later parts of this career, and I've selected this one in particular because you might recognize him. It's Ty Cobb, one of the greatest baseball players of all time. His career didn't start off so great. We're looking at the sub-objects represent home runs, doubles, triples, and RBIs. Yellow are home runs, and purple are triples. Ty Cobb was not a big home run hitter. In fact, home runs weren't really that common early on in baseball. So you won't see a whole lot of yellow geometries as opposed to some of the other geometries we're looking at here. Let me zoom out here. Okay, so I think this one that I've selected here may be New York Yankee, Lou Gehrig. Many of you might recognize Lou Gehrig's name. New York Yankee. His career wasn't quite as long as Ty Cobb, but he hit a lot more home runs. And if I reorient around here, we'll see another little grouping. A lot of large yellow means a lot of home runs. 3 guesses. This is Babe Ruth. That's the year he hit 59 home runs. The year he hit his record-setting 60 home runs is right here. But I should also be able to, actually, I'm not sure if I can do this. If I hit the U key, nope, not going to do it. Wrong file. Sorry about that. We're drilling down into that database to find more information about Babe Ruth. I'm not using that particular file. Now, some other interesting things that we might see based on the entire forest, so to speak, or the progression of teams over time. So if we look at this database from the side angle, these individual sort of walls of glyphs are actual teams. And some teams started late, which means there's gaps in the lower ends. Some teams started earlier and then ended, which means there's gaps above, time being vertical. So the earliest glyphs in this database, if I select one down here, are on the order of, like, in this case, this baseball player's name is John Anderson back in 1901. So even though we're getting kind of low frame rate, I love things like, looking at the entire forest and then being able to zoom in and drill down, and also getting a sense of change over time. Okay, so that's one attempt at visualizing an entire database. Now let's look at another very popular database that is also freely available. Let's go back to my slideshow. The Global Terrorism Database. This visualization actually uses 2 different types of glyphs. One glyph in the lower left here, even though there's a bunch of them visualized in this image, the glyph is just a squashed octahedron that's color-coded based on the type of terrorist event, and the size is scaled based on the number of people killed during those terrorist attacks. The complex glyph on the right represents all of the activity of an individual terrorist organization. In this case, I believe we've got a glyph representing Abu Sayyaf. Okay, so let's bring this visualization up. And the first thing I'm going to do is bring up, let's see, I think it's this one. This one just has a couple of terrorist groups visualized with links connected to, oh dear, I think I have ants still open. I have to quit. Oh, that's funny. No, I'm not sure why that happened. Haven't had that happen before. Oh dear. Okay, give me a moment, I can fix this. This was a change I should have made before. Okay, so it was looking for a file that it couldn't find. Whoops. Okay, now hopefully it'll run. Okay, so the global terrorism database has gone through a couple of iterations. This is the latest one as of 2015. So this is similar to the Scopus citation database spatial distribution. Thankfully, I didn't have to do the geocoding for these terrorist events. The latitude and the longitude comes with the actual event itself. If we zoom in here, you can see that each one of these are little individual octahedra. I use octahedra because frequently there's overlap. And, oh, I'm sorry, there's a question. That's a good question. The question is, how does Jeff determine what glyph design works most effectively for what data, and how much education is needed to bring the viewer up to speed on how to understand hyperglyphs? Well, trial and error is often the way I pick a glyph design. As I was mentioning with these octahedra, they work well when you have a lot of objects overlapping each other because their little edges can peek out. And if you're color coding objects, you can actually still get a glimpse of the geometries, even if they're overlapping one another. It doesn't work perfectly. Also, performance. Octahedra have only 8 facets. If I were going to use a sphere or a cylinder or a toroid, they're going to have a lot more polygons, and it really bogs down performance. That's pretty common. As far as how much education is needed, I would say a lot. Some of us are more predisposed than others in using these kinds of tools. Folks that I've tried to walk through the process have been more or less successful in doing it, but it can require a lot of hand-holding, and I would be happy to help to whatever extent I can. In some ways, I've been working in isolation, and so it'd be wonderful to have more and more people interested in getting up to speed in this tool. So thanks for that question. Okay, I just downsampled so we get a little bit better performance. You can see the legend in the back gives you a sense of the color coding I'm using for terrorist attack types. So if I upsample and show all of the events, you can see it's predominantly cyan and blue in color, which means armed assaults and bombings and explosions are the 2 overwhelmingly dominant types of attacks. You'll also see links, these colored links on the left, this fan of links. These are links for the Irish Republican Army linking the individual glyph with the events that occurred. And so let's take a closer look at the individual glyph, because the Irish Republican Army, you can see a dominant color of green in that fan of links. And that means the IRA committed more assassinations than just about anything else, at least early on. A little later on in time, which is up higher, then they went more to the armed assaults and bombings and explosions. Now, one of the interesting things about this visualization is my parent glyph is actually this little geometry down here, which is a cube. And this is apparent to all of the other geometries in the visualization. I did this because I'm using the Cartesian coordinate topology for this glyph right now. So the geometries are distributed in space in the same way they would be for the other geospatial visualizations that I did. But I can hit the J key and have these immediately wrap around a global or a sphere-shaped geometry. I also can use the arrow key. So when I hit the up arrow, it's going to jump me to the child object associated with that parent object, and that's this glyph for the Irish Republican Army. So let's zoom in here and take a closer look at this glyph, and let's get a view from this side. Okay, and I'm also going to hide this central geometry so the links disappear for a moment so we get a little bit better frame rate. So the total attacks committed by the Irish Republican Army is 2,757. Each one of these spokes and this wheel represent a particular target of those attacks. So in this case, the one I've selected is educational institutions. I can use my tab key and tab through these. And if we hit the I key to bring up the actual information associated with those, you'll see some targets are police, some targets are military, government, and so on. The child objects of those spokes, which are sort of arrayed in a shish kebab pattern, represent the number of attacks and the number killed for that particular target. So in this case, let's go up or down arrow here, make sure we've got this. So the target for these attacks is transportation. The type of attack is a bombing and explosion, and the number killed is 5, and the number of attacks is 66. This toroid, on the other hand, is a facility and infrastructure type attack. This icosahedron is an armed assault type attack. And they're all on the particular target, which is transportation. So this gives me a sense of the IRA, in sort of a quick glimpse, what their focus was, the types of attacks. So as we were aware of before, they did a lot of assassinations. And that's what these white cubes are. Now the IRA had their own mode of operation. If I hit the tab key, it'll jump me to the other. Well, thought it would. It should jump me to the other terrorist group. Not sure why it's not. Oh, I mean, oh, that's right. I've hidden it. I'm sorry. So let's arrow up. We'll unhide that, and then we'll tab over. There we go. Okay, here's Abu Sayyaf. Another thing with this visualization, being able to connect the glyph with the events themselves provides a couple of advantages. One is you can see the distribution of events over time. So with Abu Sayyaf, if I can get a good angle here, let me click that link here. If I can get a good angle, we can see most of their attacks occurred later in time. Their events occurred at a particular point in time and then continued, and their focus has been predominantly in the Philippines. So if we change our angle of view from the top down, we can see that the Philippines has been the primary target. And they have sort of a different combination of types of attacks with some kidnappings. You'll see the orange colors in there. So their mode of operation is sort of across the board. So if we look at their individual glyph, you'll see that's probably the case. So let me go ahead and select this and hide it. So we hide those guys. So yeah, there's a much more broad range of attack types and targets for Abu Sayyaf that give you a rough idea of their approach. Last but not least, let's downsample here so I can zoom in here. So let's look at a couple of features that may or may not be a surprise. This grouping of octahedra right here, if we orient from above, is the Iraq War. So this is where the vast majority of events were bombings and explosions, as you might expect. But interestingly, the higher geometries later in time include other types of events like kidnappings. Likewise, if we look at Latin America, let me reorient here. There are some interesting things that I was not aware of. Probably the most active terrorist group in the world, Shining Path, did most of their terrorist activities in Peru. And that's this grouping right here. A lot of terrorism actually just took place in Peru. Okay, so maybe that can give you an idea of how to use the hyperglyph approach in sort of a combination of ways. Now, another one that I wanted to show you, which in some ways is a great approach to interactive drilling down in data, is the human diseasome. So let me just bring this one up. go through this as quickly as possible. The human diseasome is a visualization of diseases that have common genetic components. So this is a data set that is available. If you Google human diseasome, you'll find data for Graph Network, where they provide nodes and edge data. And so I used my own approach for distributing these geometries. And the data is categorized into different types of pathologies. So there's a set of pathologies affiliated with bone. And let's set of pathologies, a lot of pathologies, and I'm getting ahead of myself here. We have a root geometry that represents the category, and this is the category cancer. Oh, and it hasn't updated. I guess I'm not sure what we're waiting for. Come on, WebEx, you can do it. There we go. Okay, green is for cancer. The circle of spheres around that central geometry for the cancer category are the actual individual diseases. So if I select one of those and hit the I key, we can see this is B-cell non-Hodgkin lymphoma. Near it is Burkitt lymphoma, and those kinds of things. This is colon cancer. Okay, so you get the idea that these are the diseases. These geometries represent the individual diseases, and then the links between them indicate that they're associated with each other. They have genes in common. So now if we tab over to developmental, I'm just going to give you one quick example of how I use this. These are developmental pathologies, and there's one up here that has a strong connection. If we zoom back and reorient, it has a strong connection with ophthalmological, which is eyesight, basically. So we might imagine, and I don't know if I'm assuming that that's obvious, you're seeing these these yellow links sort of strongly directed to ophthalmological diseases. So I'll just select that and zoom in so you can see all of those yellow links from that one disease under the developmental category. And then we would assume that that one disease must have something to do with vision. So what is that disease? Well, it's, we can get a good angle here, Peters anomaly. Okay, if we want to know more about Peters anomaly, though, one of the nice things about this tool, hitting the U key, it calls a script, PHP script, goes into the database, returns the results, and then it actually performs a query on PubMed. So we can see some of the results on PubMed associated with Peters anomaly, and we can see clearly that it's affiliated with eyesight, glaucoma, long-term clinical course in eyes with Peters anomaly, that kind of thing. So interactivity can be really valuable. You can get a big picture of connections. There's another interesting connection between let's see, endocrine and cancer. This disease up here has a lot of green links to the cancer category. Let me make sure I'm picking the right one here. And what would that be? That is hyperparathyroidism. And yeah, thyroid cancer is fairly common as well. Okay, so that's the human diseasome as a demonstration of interactivity and drilling down a little bit further and using the forest to get an overall vision of the data set. Now, there are other visualizations that I'm going to skip past, actually, because I'm behind. The Angola Civil War visualization was one of the first that we did. A woman by the name of Jen Zeinke was kind enough to provide the data that she used for her PhD thesis in trying to understand the Angola Civil War. That visualization is available on my website. You can download it. Likewise, the Syrian Civil War, we've done other interesting visualizations using, sort of medium complexity hyperglyphs. You've seen the synesthesia. Okay, so a couple of things I want to show you real quick. These are sort of arbitrary forest distributions. ISAT is the Information Science and Technology Advisory Group for the Department of Defense. And it's an annual meeting. It's invitation only. And Dave Warner is a member, or was a member, and thought it would be fun for the annual meeting to visualize all of the members' biographical information. So I gathered all the biographical information for all of the ISAT members, parsed it into a series of geometries, and that should load momentarily. And so this isn't any kind, this is just a grid, an XY grid. There's no meaning to the distribution except alphabetical, actually. So let me make sure you're seeing what I'm seeing. So if we zoom in here, here's the glyph. The root glyph identifies the ISAT member's name, Anant Agarwal. These subglyphs provide an insight into the number of studies related to ISAT that they've performed. Other parameters affiliated with their biography in a similar way as the topic space visualization that I had done with the DTIC database. And then there's this other kind of glyph subobject that I thought I would take a shot at that's supposed to represent how long they've been members of ISAT. So the taller this long rod, the longer they've been members. And you'll see most members have a pretty active or fairly complex hyperglyph. There's some information online that I was able to gather, but you will see the occasional member that has really no information, and yet they've been a member of ISAT for a long time. And we like to joke that we've found the Fed. This is somebody who's a veteran, but there's really very little online that you can find about them. This is, I think, this is not Al McLaughlin, George Hellmeyer. If you Google, there's Al. I think that's Al right there. Nope, that's not Al either. Okay, well, so much for me trying to find Al. But these are the guys that have been around for a long time, but they just have a very, very sparse web presence. So we got a kick out of this kind of an approach. I'm going to move on to another one that was done as part of the Washington, D.C. visualization meetup group. Where's this one? Yeah. So this is an interesting visualization in which I tried to characterize the different visualization applications. So it's sort of a meta visualization of visualization people. Let's take a look at this one real quick. So my goal here was to get a sense of the most popular visualization tools and who's using them. So meetups generally provide their moderators access to their personal data. And I picked the wrong one here. Let me reorient. Oh, and you're not seeing what I'm seeing. Okay, so what I've got here are large geometries with links. Each one of these large geometries, let me get a better viewing angle here. Each one of these large geometries, in this case a pink tetrahedra, this represents the number of D3 users that are part of this meetup. There's 79 D3 users. This blue octahedra represents Tableau. There are 75 Tableau users. This big icosahedron, represents R. By far, there are more R users, and R isn't necessarily a visualization tool. It's a sort of a statistics tool, but it's got some real powerful visualization capabilities. Not a lot of users of MATLAB. Illustrator, I was surprised to see Illustrator was even in there because that's a graphic design tool. And Excel, of course, Excel is sort of the standard. So we can get a sense of who's using what. And then if we drill down the individual geometries, we can get a sense of who's done what, who's attended which meetups. So in this case, this user is Ricardo E. He joined in February of 2013. He has RSVP'd to 3 meetings. He has said yes and he has attended 2, and he's canceled on 1. You can also get an idea of where the bulk of your users are. So I've got a map in this visualization, and most of the users are centered in Washington, D.C. itself, but you'll see that there are links going off screen. I geocoded the hometowns of all of these members, and so these links actually go off into latitudes and longitudes that are way too far for me to actually browse to. But you can get a sense of how far-reaching this meetup group is. And I think one of them is me. So I like this in characterizing individuals, sort of the hyperglyph of a person's interests, to really ram that home. I've got one last visualization here of a real interesting data set that was built by a survey that was distributed by Red Bull in collaboration with a sociobiologist, Eric Berlot, called Hacking Creativity. Some of you might actually be aware of the Hacking Creativity survey. It was a survey of about 110 questions that they sent out to creative people of all walks of life to try to better understand how they got their inspiration, under what conditions they were creative. This is by far the most complex glyph that I have ever designed, and it's probably too complex. So what I did was each one of these survey submissions, the participants categorized themselves into one kind of category, such as cerebral or self-confident or ideator. And so what I've got here are clusters of participants in this survey based on the categories that they were predominantly niched in. So if we step through here, we can get a sense of the categories: kinetic, perfectionist, multitasker, kinetic, driven, solitary, doer. Some of them have more members than other: kinetic, pragmatic, multitasker, evaluator, and you get the idea. So this category in particular has 119 members, so to speak. In other words, 119 people who submitted the survey fall into this category. And it also contains the participant with the most connections. So Eric Berlot ran some graph analytics on this data set to try to establish connections with other participants. And that measure of connectivity is referred to as degree. So this big green sphere represents the degree of this user. So if we zoom in here, I've displayed the information associated with that sphere. You can see that this participant is connected with 64 other participants. I'm going to hide that sphere because it's overwhelming a lot of the other geometries in this glyph. I'm going to select the central parent root glyph, and I'll show you the information affiliated with that user. And then let's just take a closer look at this particular user's interests. This glyph has data on the user's workspace. So for example, let's grab a glyph over here. I'm actually importing textures to represent different things like desktop clutter. So this particular user or participant described their workspace as average tidiness. And this graphic is supposed to sort of graphically represent average tidiness. They were also asked questions such as, where is their most common producing space? So this circular toroid here has subgeometries that represent where they feel like they're most creative in terms of their producing space. And in this case, this user claimed that their domestic spaces, their workspace, their public spaces, and if I can navigate to the other one, nature and wilderness. So this user seems to find a lot of spaces in which they're creative for the varying categories. I'm not going to spend a whole lot of time on this glyph. I would say it's probably overkill, but I got just about all of the data for this particular survey visualized in one single glyph. So there are other things like cups of coffee. So yeah, this visualization down here, I think this glyph down here represents the number of cups of caffeine they have during the day. The one next to it represents whether they use drugs or alcohol, and this one claims occasionally. So those kinds of things are all part of the survey, scaled based on degree, and then associated with links to other participants. Another nice feature I believe I've got working with this particular visualization. Oh, no, I don't. Can't drill down to learn more about the, no, it's not working. Okay, so that is sort of glyph as person. The last thing that I'm going to show you, make this really quick, glyph as event. This is a visualization of 4 days of data acquisition during a Red Bull event called Project Endurance. Red Bull wanted to better understand how to use electrical and magnetic brain stimulation to eliminate fatigue in endurance athletes. So they recruited 4 world-class endurance athletes over the course of 4 days and gathered all kinds of physiological data. So what you're seeing here from left to right is a timeline, and each one of these 4 groupings horizontally represent the activity and the data collection for each one of the athletes. So the first athlete down here at the bottom is Rebecca, and if we select this first leftmost cone, this represents when Rebecca arrived. So she arrived at 7:45 in the morning. The first thing that they did was they collected a battery of physiological measures using the in-body physiological metric system, things like metabolic rate, blood glucose content, and those kinds of things. This was just an arbitrary way of representing that kind of data, body fat and those kinds of things. Then they got on a bicycle and started riding the bike. And at certain points during that bike ride, they were zapped with electrical stimulation on their brains. And the hope was that as they began to get more and more fatigued, the electrical stimulation would reduce the perception of that fatigue. So in order to better understand this data set, what we've done here is introduced sort of metaphorical geometries that represent different points in time. And when I hit the U key to drill down, it actually brings me to a web page with more conventional types of visualization. So in this case, this is a PHP plot of Rebecca's EMG data. And when I select this plot, it actually brings up a D3 visualization where I can drill down even further. I can click and drag a slider and then scale that plot up and get even more detail. And so this is a visualization of glyph as event. I would say this is really the most complex glyph I've ever visualized. Some of it is actual data, like these glyphs down here represent real physiological data and provide the ability to bring up 2-dimensional plots by hitting the U key again. So this is an example of event as glyph and interactivity and drilling down as well. But I'm out of time. So I'm going to go ahead and stop there. I look forward to sharing as much or more information as possible with those of you interested. If you reach out, my contact information is not on a slide. My apologies, but I'm sure we can find a way to get you in contact with me. So thanks very much. If you have any questions, go ahead and post to the chat. And that was.
Thank you, Jeff. That was a very exciting presentation. If people want to learn more, do you have references or pointers you might recommend?
Well, yeah, I don't know how to make my slides available, but I do have a slide in my presentation with a lot of links. So I can leave that up, and I can make that available one way or the other, however you think is most useful.
We're going to post all the slides so people will be able to access them.
Okay, yeah, so that link right there, or that slide right there, has a lot of great links.
Okay, it doesn't look like there are any other questions at this point, so please join me in thanking Jeff for a great presentation today. And we really appreciate your time and effort. Our next webinar will be next week, Wednesday, June 28th by Ilya, and it'll be titled on the topic of Viking. There are no webinars in July due to other competing national events, conferences and whatnot, but we'll be back in August. Check our webinar website for those dates and events that are coming up. You will receive a very short 5-question survey. We appreciate your feedback to help us to improve the webinar series and to give Jeff feedback on his presentation as well. So with that, no other questions. Thank you, everyone, and we hope to see you again in the next webinar session.